Today I shall present something on numerical issues, on numerical solutions to fractional order control systems. And in this lecture I will give you some details of how to solve the problem in Matlab. And the topic of today will be given as follows. And in early talks, and I think Professor Chen and Professor Li presented something in theoretical way about about the analysis and of fractional order calculus and the fractional order systems. And now my question is, how can we solve this kind of problems by the use of computers? And in this part, we will use the so-called Matlab, that is modeling, analysis, and design. First, I will talk about the modeling of fractional order systems. How can we represent the model in Matlab? And then, I will talk about how can we analyze a fractional order system. That is the frequency domain analysis, the time domain analysis, as well as stability analysis. How can we do that? And then we should talk something about how to design controllers. But this part not only for fractional order systems, but also for integer order systems. Just some ideas. As the first part of the Matlab, we will talk about the linear fractional order transfer functions. How can we represent a linear transfer function in Matlab? And I designed a toolbox called FOTF, that's for fractional order transfer function. In this toolbox, there is a class or object defined to describe a fractional order transfer function. And based on the transfer function, I'll tell you how we can calculate the interconnected fractional order systems, and then how can we analyze fractional order transfer functions in time domain or frequency domain. And then I will talk about the analysis of fractional order systems that include the Matlab functions and analytical solution to fractional order differential equations. And then we will talk about the stability, time domain analysis, and frequency domain analysis of the fractional order systems. For nonlinear systems, I will introduce a block diagram-based simulation method. And then I will talk something on how to design controllers. So let's start. In this talk, I will give a systematic view on the MAT process, modeling, analysis, and design process. And I will not say too much in mathematics, but concentrate on the solutions using MATLAB command or MATLAB toolboxes. And for linear systems, I shall describe how to design a FOTF toolbox and how to use it, and then how to analyze a given system in fractional order. And for nonlinear systems, the only way I think is to use simulation method. And then I will talk something about optimal controllers. So the first question is why we need a toolbox to describe a fractional order transfer function, or why we need such a one for the analysis of fractional order transfer functions. For integer order systems, there is an existing toolbox in Matlab, which is the widely used control system toolbox. And in this toolbox, it allows you to represent a transfer function in a very simple way like this. And then you can use multiplications, plus, or feedback functions to define the series connections, parallel connections, and then feedback connections of transfer function blocks to form an overall system. And for the analysis part, they provide functions like bold, Nyquist, step, such kind of commands which can be used to analyze integer order systems. So I think similar things should be done on fractional order systems, and I prefer to use this similar command for fractional order systems as well. So now let's consider the linear transfer function of fractional order. Before we talk about linear transfer function, we will first consider linear fractional order differential equations given like this, where we have different differentiators for the signal y, which is the output of the system, and for the input of the system u. If the initial conditions are 0, then Laplace transform to the signal y can be used, and the property of this one can be adopted. That means when the system is at rest in the initial stage, in the initial time, which means the initial value is 0 and the velocity of such kind of thing are also zeros. So in this case, we can use the property of Laplace transform, and by the use of Laplace transform, we can define a fractional order transfer function like this, which is quite similar to the case in integer order systems. And in the transfer function, we noted that there are coefficients in numerators and denominators, and apart from that, there are also orders in numerators and denominators. So to describe uniquely a transfer function of fractional order,